I presume that you can all ramble off Newton's 3 laws. You should also be able to ramble off the 3 Kepler laws. The orbits of planets are ellipses, with the sun at one of the foci. Yeah, the second law. The planet sweeps out an equal area in an equal amount of time throughout its orbit. Third law. The period of
period squared proportional to the
semi-major axis cubed.
Yes.
Yeah, okay, so educated
You
physicists
were also in it.
can spout off Kepler's laws. Okay, so let's write them down again. So Kepler's 3 laws are, if I have an orbit, and I have a small object here, the small object is called the satellite. It has little mass, little m, and then there's the big object, which has mass, big M. The big object is at one of the foci of the ellipse. There's a semi-major axis and a semi-minor axis, A and B, of the ellipse. So law number 1, orbits are ellipses, which we will learn is kind of good enough for the solar system, but not exactly all the possibilities. Law number 2 is equal areas and equal times. And you could read in the book about a nicer way of saying it. But the idea is that if I go from here to there, and this is some area A1. Oops, that's not the area I want. The area I want is here to there. And then over here, I'm going to go, say, from here to there. A2. And this is 1 week. This will be 1 week. God, I didn't spell today. So if my satellite travels for 1 week that way, it'll sweep out a certain amount of area. When it gets closer, it'll go faster. It'll sweep out the same amount of area. And we'll prove that in a few minutes. And 3, that the period squared is proportional to A cubed. So T being the period, or 1 year in the case of the Earth. Right? Don't be the student who comes and asks me what's the period of the Earth's orbit on the test. It's like I was doing 244 once, and I had a problem, said a meter stick goes flying by a speed of 0.8 c. How long does the meter stick appear to be to the occupants of the room? The student comes up and says, "How long is the meter stick?"
Well, did you give a velocity? Because typically they take into effect.
But the astrometer sticks are like the really big ones that are like 2 meters long.
Yeah, the really big meter sticks are 2 meters long.
That's called a 2 meter stick.
No, it's not. It's still a.
Yeah, whose definition of a meter?
All right.
Everyone's. That was the question.
Wow, so angry today.
No, just very honest.
Okay, so Kepler and Copernicus and all of those guys were alive before Newton, right? And so they calculated that the orbit of objects were ellipses without having any physical understanding for why the orbit would be an ellipse, right? Newton writes down a gravitational force law, then invents calculus, then can prove that the orbits are ellipses. Okay, so it's sort of the historical thing of everything is a little bit bundled up. We are the beneficiaries of being able to start with the Newtonian force law and derive Kepler's laws. Kepler's laws were observational laws, right? He looked at the data and he observed these things. We should pay homage to the people before Kepler and Galileo and others who we now think of as dunces, right? So the people who thought that the Earth was at the center of the solar system had no observational recourse that would prove otherwise. Right? So before Galileo, it was okay to think the Earth was at the center of the solar system and that planets went around the Earth in really crazy orbits. Okay? Stars go, no big deal. Planets go and do all sorts of crazy backtracking motion, particularly Mars and other planets that are outside of our orbit. Right, because as we pass them, they look like they go backwards for a little while. There's a retrograde motion of Mars. Okay, and they knew this, and so they had to build in these little epicycles to make it work. Okay? But if you don't have a physical explanation for why the planet's motions are what they are, if you don't have Newton's laws, you don't have a gravitational force law, you don't have any reason to believe that the stars aren't just some wacky thing. Alright, so we should pay homage to the fact that they figured out all these little mechanical epicycle things. It's clever engineering, good observational note-taking. The only things that you can start to prove from Earth, before you get into space, that the planets are orbiting the sun is to look at the phases of Venus. So because Venus is interior to our orbit, it is impossible for us to see a full phase of Venus. Is that true?
Yeah. It has to go on the other side.
It's got to be on the other side. Does that make sense? Right, so when you look at the moon, and the moon is a full moon, it's because the moon is turning its spotlight on you. Because the moon is fully reflecting all of the sun's light back to you, right? Is there a dark side of the moon?
Only from our point of view.
Right, so there's never a side of the moon that's always in darkness. You understand that, right?
Temporarily.
There's just one
There's the side we don't see,
Yeah.
but it's not always in darkness.
As a matter of fact, it's very bright when there's a new moon.
Right, there's a new one, it's very right,
It
that's
has
right.
opposite phase.
Right, so Galileo claimed to have seen the phases of Venus, which is pretty unlikely. And if you ever get a chance to go to London and go to the Royal Observatory and go look at the equipment these people were using, you know, even 100 years after Galileo, you can imagine these people sitting there for 18 hours, you know, or 8 hours all night, squinting through these old telescopes to make measurements of things. You can understand why they got so many things wrong. Or they thought they saw stuff they couldn't see, and, you know, it's... Anyway. Alright, so everything is based on Newton's gravitational force law. So we have some mass m, some other little mass m. There'll be a center of mass. And these two objects are going to orbit about their center of mass. We're going to let capital R locate the big object and little r locate the little object. And you can put the origin anywhere you want in the universe, which is why it's okay for the Earth to be the center of the universe.
Huh.
Think about that for a second. Alright. Because the universe is isotropic and homogeneous, it's perfectly fine for the Earth to be the center of the universe. So you can put the origin wherever you want, so the smart place to put the origin is at the center of mass. You put the origin at the center of mass. The formula for R center of mass is capital M R plus little m R over m plus little m. This is a weighted average. So the center of mass definition is the weighted average of position vectors. So you got one position vector, capital R, you got another position vector, little r. You choose to add them up such that the mass you move them towards the more massive thing by multiplying by the mass. If the masses were equal, the center of mass would be in the middle of the two objects. Right? That makes sense? Feel good? Alright. If we choose to put the center of mass at the origin, then we can solve for r. And we get r is little m over big M over r. Alright? Feel good? So for the Earth and the Sun, because the Sun is so much more massive than the Earth, the center mass of our two bodies is well inside the center of the Sun. The center of mass between me and the Earth is very close to the center of the Earth. It's not quite the center of the
It's
Earth,
not by a little bit.
right? But it's very close to the center of the Earth.
Maybe not that much.
Right, so, you know, the Earth is 10 to the 24th kilograms. I'm 10 to the 2nd kilograms. Yeah, I'm 10 to the 2nd kilograms. So, the center of mass is 10 to the minus 22nd meters towards me. I move the world.
Yeah.
You should make a motivational poster about that. You move the world.
Right, which is why, you know, when you jump, the Earth doesn't move dramatically,
But it does move.
but it does move.
Which,
Wait a second, no, because you push off too.
Well, but then there's just as many people in Australia
you recoil, and if it recoils, it's a difference of your. Is how far the number.
But it also means that
mass.
it also means that I can push it down. You can push there.
So,
Right, but then you are connected by gravity and you attract it back that distance as you come back down.
so you got everyone in the world to like go to the same city.
Okay,
jump at
so
the
you take
same
one time
time.
derivative of this relationship, we find that the velocity of the big object is small compared to the velocity of the little object by ratio little m over big M. If I then look at the kinetic energy of the big object, that's 1/2 big M big V squared. So that's 1/2 big M little m over big M squared little v squared is little m over big M 1/2 little m little v squared. So the kinetic energy of the big thing is little m over big M, the kinetic energy of the little thing. Our friend, the ratio of the masses. Okay. Same thing if you do the ratio of the angular momentum. The angular momentum of the big object will be the angular momentum of the little object multiplied by little m over big M. Woo! Okay. So the point here is that if you have one really massive thing and one thing that's not very big at all, then the really massive thing is basically at the origin, it's at the center of mass, and doesn't move. It doesn't have any kinetic energy, even though it's really massive. And it doesn't have any angular momentum, even though it's really massive. And it's moving a little bit. So the angular momentum relative to the center of mass is all in the satellite. The satellite's the little mass object. This sort of makes sense to everybody? You good? Alright, so. La-di-da-di-da-di-da. Lots more details in the notes. I'm more eloquent. I was actually falling asleep while I was writing the lecturing through the last
big
section.
yawn.
You heard me yawn. Oh, God. I'm working too late at night. Alright.
You know, I thought it was so
In
funny.
what I was saying, really.
Somebody walked in while I was listening to the lecture and like looking at the notes. They're like, "What are you doing?" So I showed them, and they were like, "Does he have an English accent?" I think it was the music in the background. I just assumed.
Alright. So now, let's prove the second law.
What's that prove the first law?
Alright, so if I have a orbit here, and I take a very, very small angle d theta. So that so this line over here is really a straight line. So now I got a little triangle. How much area does my triangle have? Well, h is approximately r d theta. And the little bit of area that my triangle has is 1/2 RH is 1/2 r squared d theta. So that's the area of my little triangle for my little area d theta. Yeah.
Why is it approximately r theta? Because isn't that the arc, not the...
Yeah, okay, so that's the arc length. So, well, there's this little bit, h is really the length of the arc. But this formula 1/2 RH is 1/2 base times height is a triangle formula for an area. Gotcha. So I'm tossing them down.
Okay.
I could probably be more precise. This is probably actually the answer if I'm really careful about what I'm doing. All right. Now, let's take dA dt. So dA dt is 1/2 r squared d theta dt. And let's multiply by 1 in the form of m over m. And so what I have is 1 over 2m mr squared d theta dt. Mr squared, you all recognize, is the moment of inertia of a point mass. Right? D theta dt is the angular speed. So this is equal to 1 over 2m I omega. Right, where I is the moment of inertia. In other words, dA dt is 1 over 2m times, well, it's the angular momentum over 2m. And since the angular momentum is conserved, then dA dt is a constant. Which means you go in equal area in equal time as you go around your orbit. Right? You know, so you can do all the things which people get wrong. Right? So in the I guess I can say it wrong that way. So in the summer, you're closer to the sun, and so when you're closer to the sun, you move faster, so the day is longer. You guys like wrong on all 4 fronts. Like all 4 statements are individually wrong. Right? Why do we have seasons? The tilt of the Earth. In the summer, the northern hemisphere is tilted towards the sun. Is it because the northern hemisphere is closer to the sun that it's hotter? No, it's because the sun is more overhead. And the more directly overhead the sun's rays are, the more absorbed energy you have.
The Earth is actually kind of, it's farthest.
Yeah, but that doesn't really matter. Yeah, it might be.
So where is the other foci